Let's remember a few results about the exponential distribution. We'll assume that the random variable x is distributed according to the exponential law with parameter lambda. This means that the probability that x is greater than a threshold small x equals exponential of minus lambda x. It can be shown that the expected value or mean value of x equals 1 divided by lambda. It can also be proven that the variance of x, defined as the difference between the expected value of x squared and the square of the mean value of x, equals 1 divided by lambda squared. The squared coefficient of variation of x is defined as the ratio of the variance of x to the square of its mean value. Note that, whatever the value of the parameter lambda, the squared coefficient of variation of an exponential random variable is equal to 1. One very important property of the exponential distribution is the so-called memoryless property. Consider an electric bulb with an exponential lifetime. Whether it has been used for 1 day or for 1 year, the time that remains until it will fail is distributed according to the same exponential distribution. This means that the past lifetime has no influence on the future lifetime of the bulb. It will not wear out. Now, let's go back to our customers. If they arrive according to a Poisson process, then the interarrival time between two consecutive customers is an exponential with parameter lambda. Assume that an external observer knows that the last customer has arrived u0 time units ago. From the point of view of this observer, the time until the next customer arrives is distributed according to an exponential distribution with parameter lambda. Knowing that the last customer arrived u0 time units ago does not bring any useful information to predict when the next customer will arrive. The memoryless property of the exponential distribution can be stated mathematically. Before we do so, let's remember that if A and B are two evens, then the probability of A given B is defined as the ratio of the probability of A and B, or A intersect B, to the probability of B. If ui is an exponential random variable with rate lambda, then the probability that ui is greater than u plus u0, given that ui is greater than u0, is equal to the probability that ui is greater than u. This quantity equals the exponential of minus lambda u. This is the memoryless property of the exponential distribution. Another important property of the exponential distribution is the law of the minimum of two exponential random variables. Let's assume that u and s are two independent random variables such that u is an exponential with parameter lambda and s is an exponential with parameter mu. Let's consider z, defined as the minimum of u and s. In particular, in a queuing system context, if u is the time until the next arrival and s is the time until the next departure, in other words, an end of service time, then is the time until the next event in this system, whether it's a departure or an arrival. One remarkable property is that z is distributed according to an exponential law, and that the parameter of this exponential law is the sum of lambda and mu. Let's look at the probability that the next event is an arrival. Another way to say that is that s is equal to u. It can be demonstrated that this probability is lambda divided by lambda plus mu. And what about the probability that the next event is a departure? Well, this probability corresponds to z equals s, and it turns out to be mu divided by lambda plus mu. And the first case corresponds to u less than s, or arrival before departure, while the second case corresponds to u greater than s, or departure before arrival.